Hi guys. Right, I was thinking this was the last video I was going to do on rates, and I've covered the concepts and some of the difficult stuff, and I think I've got two more things to perhaps look at. Okay, there's this video which is about rates and mechanisms, and then there's one more about something called the Arrhenius equation, which we will look at later. This is rates and mechanisms, and what it comes down to is this. We can take an equation and we can do experiments by leaving the concentrations of, say, two of the reactants the same and changing one thing at a time and looking at the rate, having some way to measure and monitor the progress of the reaction and then calculate the rate from the gradient. Then we can do another sequence of experiments and we keep two other things, we keep two things the same and change something else and look at the effect on the rate from that. And you've used data to be able to develop the rate equation. So you can see how each reactant affects the overall rate. And some reactants affect the rate very significantly because they're second order. So if you double the concentration of that reactant, the rate is 4 times greater. If you triple the concentration of the reactant, 9 times. 4 times the concentration of that reactant, the mechanism, the rate will be 16 times more. Okay, so it has huge influence on the rate of the reaction. Yet it's only one of the components in the overall equation. Okay, you couldn't look at the equation and say that that particular reactant has such a significant impact on the rate. You can only do that from doing the rates experiments. Another reactant that's perhaps one of the 3 or 4 reactants in the overall equation, you may keep the others the same and change that and find that that's first order. It has a significance upon the rate. Okay, so you double the concentration of that reactant, you double the rate. 3 times the concentration of a particular reactant, 3 times the rate, 4, 4, 5, 5. So it's influencing the rate. But there may be another reactant on there, and you keep the others the same and you change that, and it has no effect on the rate at all. Okay, maybe it's in excess, or maybe it has to be there, but the concentration of it does not affect the rate of that reaction. It won't appear in the rate equation. So the rate equation gives you so what's the point of doing all this? Okay, well, you can then develop the rate equation. And the rate equation gives you an insight into how the reaction proceeds, because the reaction does not proceed as the equation suggests. A reaction might go through various intermediates. It might go through all sorts of what we call steps, different steps, before the reactant's eventually formed. So there's a whole sequence of steps, and it's important for chemists to understand the sequence of steps and how particles collide to make intermediates and how the reaction actually proceeds, rather than just what happens what reactants you've got at the start and what reactants you've got at the finish. If you can fill in what's going on in the middle, you can maybe influence that reaction, maybe use a catalyst to speed up that reaction, maybe develop a way to make key particles collide and alter what they do. It gives you much more of an insight into the reaction, and then you can develop it and experiment with it and research it in more detail. So that's why we do rates, to give us far greater insight into the reaction. You are expected at A level to look at an overall equation and look at a rate equation and use that to develop a possible mechanism for the reaction. Okay, this is the sort of the last of the sort of rates questions that you're going to get generally. I mean, there are few other things. There's always other things, but this is what it all sort of is working towards. Developing some kind of mechanism and coming up with some idea of how the particles react. Okay, and basically the questions come and you answer them. I'm going to give you some examples, talk your way through them, and then try and do some yourself. They're not that common on papers, but they do appear once every couple of years for sure. Some are easier than others, okay? But I'll give you the idea of how to do it, and then you see how you get on, okay? So, this is called rates and mechanisms. Okay, so let's have a look. Here's a reaction that looks to me like a reaction that's absolutely spot on to analyse and develop the rate equation. So iodide, aqueous solution, so we can alter the concentration of that, plus iodate. They love these disproportionate reactions. Okay, plus iodate, so there's a positive oxidation state of iodine in that, so that screams disproportionation straight away. In fact, would do you no harm to develop to give the redox equations for this. Okay, plus acid. Again, you've got 3 reactants there, all of which you can tinker around with, but ultimately, the products that you get from this reaction are iodine. So it'll go darker as the reaction proceeds. We've done this loads of times. That's your way to monitor the progress of the reaction and calculate the rate. Your visible quantity, your measurable quantity, plus water. Okay? Now, that is as I keep saying, that's the molar ratio of the reactants and the molar ratio of the products. If you like, the beginning and the end. What goes on in between is what the rate equation informs us of. Okay? This is not how the reaction proceeds. This is the starting and the final. And they will ask you this, why is it unlikely this is how the reaction proceeds? It's unlikely because for this to happen in one step, you're going to need 11 particles colliding simultaneously. Simultaneously. 5 of those, and 1 of those, and 6 of those all coming together in one great big step, all reacting, bang, like some kind of magical thing, and coming out with the 2 products there. That is not a likely thing to happen. That is 11 particles all hitting each other at the right velocity, at the right angle to produce those products seems highly unlikely, which is why this does not tell the whole story. Only the products and the reactants in their molar ratios. So you would use that, and you may be asked to do that in an exam question. You'd be given rates data, maybe graphs, maybe in the form of graphs, maybe in the form of a table of data, but you'll be able to deduce the rate equation. Now, the rate equation for this reaction is rate is equal to K, rate constant, iodide, second order. So that obviously the concentration of the iodide is vital to the rate. Okay, second order. This iodate, first order. Okay, I'll put 1 in. Okay, and acid, second order. So that will tell us about how the reaction proceeds. So the rate equation is, I suppose, so that rate equation gives us, we can do some kind of mechanism from a rate equation like that. Now, that example is probably a bit hard, so what I'm going to do is give you some A-level examples of this, and hopefully it will come together. So this is unlikely because you're talking 12 particles colliding. this will tell you some kind of intermediates, but it's much harder than probably you're going to get in the exam. So let's do a couple of 3 exam ones. Okay. Right. Okay. Deduce question. Deduce the possible mechanism or the steps within the mechanism. That's what they want. Okay? And I've never seen one with 3 steps. I've only ever seen questions with 2 steps in them. Okay, which is far more simplified than the real world, but that's bad enough. Okay, so we stick to 2 steps. So let's have a look at this. Here's an equation, hydrogen, right? I'm not interested in state symbols for this, I'm not interested. Plus nitrogen monoxide, you don't have to remember these weird equations, you just have to be able to analyse them. Makes nitrogen and water, okay? Again, we're asking 4 particles to collide there to make nitrogen and water. In 1 step, no. Okay, those are the reactants, those are the products, end of. This was analysed, a rate equation was created. It was found to be this, okay? Hydrogen in there, first order. Nitrogen monoxide, second order. Now, notice that this rate equation is easier than that, okay? This is much more likely that you're going to get. This is just to illustrate the I don't know really, just to illustrate the difference between the 2 equations, right? So, focus on this. Second order, NO, right? First order, H2. The question would be, deduce a mechanism, a possible mechanism for this reaction. Right, 2 steps. Okay, in those 2 steps, you have this. You have a slow step. This is the step that takes the time. This is the step that is the dominant step that determines the rates. The first step must follow the rate equation because it's the slow step that really dictates the whole rate of the experiment. And we call it the rate determining step. RDS, the rate determining step. And then there is a second step, which is the fast step, that, if you like, has to match the overall equation. To match, you'll see how this works. Overall equation. That's what you've got to remember. Slow step that must show, which must show the influence of the rate equation. Fast step to match the overall equation, and you're going to form an intermediate, which then gets cancelled out. That's always the way. So, let's have a look. Go to the rate equation first of all. 2 steps. Step 1. Step 1 is the rate determining step. So step 1, I must use the rate equation to deduce step 1. Now step 1 says that if it's second order, right, it tends to mean this. So I've got to put this in a sort of an equation. Right, second order and first order. Right, what that means is this. If it's second order, 2 particles of nitrogen monoxide will collide, because that doubles their influence in terms of the rate. That's what causes that second order relationship you're aligned on. So that obviously the concentration, because there's 2 particles of colliding, is much more significant. First order with hydrogen, 1 particle colliding. That you can always do straight from the rate equation. If it's second order, 2. If it's first order, 1. Arrow. You're going to make something. Okay? Leave that blank for now. Right, then we look at the next possibility. The second step tends to be fairly straightforward because the second step, we've sorted the rate equation, we've covered it. The second step is the fast step, which purpose is to match the overall equation. Okay, so if you look in the overall equation, I've got 2 of these and I've got 2 of these. Okay, that's the ratio of moles that react. So by doing the rate equation in the first step, the rate determining step, I've covered 2 of those. Second order, 2 smash in, and also 2 in the overall. So that's good. One particle collides because it's first order with hydrogen, so it's in there. If you match it up with that, this is a bit tricky. You will find that I've got 2 there and there's 2 there, so that's good. I've got 1 there, but I've got to have 2 in the overall equation. So I've got no choice other than to put hydrogen in here as my second step. Because if I add this side together, 2 of those and 2 of those. But that one's not in the rate. If it was, it would be second order for H2. So there's only one of them in the rate determining step. Okay? Right, now you've got to use a bit of your brain to try and work this out if you can. I look over here. I've got to make nitrogen and I've got to make water. Now one tip may be I've got to make 2 waters, okay, in the overall equation. So maybe 1 water made in that one and 1 water made in that one. Okay, try that. Now, combining these must match the overall equation. So, how am I going to do that? Now, I've got to make some nitrogen as well, right? So, if I make some nitrogen here, okay, if I add these together, right, I'm going to be fine to make the overall equation. Okay, I'm going to be fine because I've covered the rate equation. So the whole key of this is to find an so it's all covered, but these equations are not balanced. Okay, something is missing, and that something is an intermediate that then cancels out. So because as it stands, that's fine, but there's a gap there and there's a gap there. This is when you've got to think. Okay, so what sort of intermediate could I make here that will satisfy things? Well, H2, H2, 1 O's gone. Now, it doesn't matter what you make. I'm going to write it in red. It doesn't matter at all. But what's left over here is N2 O. Okay? That is your transitory temporary intermediate. Then, so it makes that and it makes that. You come up with that yourself. Then, plus N2O. You've got to, if you have it there and it's not in the overall equation, it's got to be here. It's something that will cancel out both sides. So that what you're left with matches the overall equation and the rate equation. So N2O goes in there. Okay, that means overall it will cancel out. Right, but that's your intermediate that is formed or could be formed, possibly formed within within the mechanism of that reaction. So let's just see if it balances that. So N2O there plus H2O, fine. H2 plus N2O, right? Makes, does it balance? Yeah, N2 and H2O. Add them together and you will end up, if you go down here, with that and that. You've answered the question. You've discovered the intermediate. That's how you do it, okay? They look a bit tricky to start with, but we'll do a few, right? How about this one? Try and do these yourself. An overall equation like this, right? So number 2, hydrogen plus some weird stuff, iodine chloride, not interested, okay, makes 2 hydrochloric acids. There's no right or wrong answer as long as it matches the criteria. There are always different ways to do these, okay? But anyway, hydrochloric acid, 2 of them, plus iodine. Overall reaction right there. That was analysed, and this was the rate equation that was discovered. Rate equals, okay? H2 ICL. Right, stick to your guns, stick to your guns, stick to the process. In a way, it's harder to explain than to actually do. So, right, first step, rate determining step, step number 1. Go to your rate equation. That defines the first step, right? Right, so here we go. H2, 1 particle, that's what it's telling us, collides with 1 particle, not 2, like the way before, because there's no second orders to make. We'll sort that later. Then you go to your overall equation. The overall equation, I've sorted the hydrogen in its first step, and I've dealt with 1 of these ICLs, but there's 2 of them. So I've got to put another one in here. Right? There. So when they're added together, I'm covered. There's a gap. That gap will be this intermediate that will then cancel out to give you the whole overall equation that's hidden within the rate. Okay? So, different ways of doing this. This is when you have to think and you have to play. I've got 2 HCLs here. There's actually no, as far as I can tell, there's no sort of way to you just have to think about what you've got in front of you. Okay, so I've got 2 HCLs. So how about I'll put an HCl in the first one and an HCl in the second one. Seems reasonable. Okay, so that, when they're added together, give me 2 HCl. I know I've got iodine left. Okay, so I need to make some iodine. Right. How am I going to approach this? Go to red for the intermediate. If I do that, make HCl, I'm going to have HI left. So I'll shove it in there. Nothing else can be. Okay? So, that HI, which doesn't appear in product order, it's hidden. Okay? It's got to go here. It's got to cancel out. Put the HI in there. Now, with a bit of luck, I've done it. Right, what I mean is this. HI, right, that will make that. That's perfectly balanced. That matches the rate equation. That cancels with that. That's fine. Okay, there's one thing missing, which I'm going to have to put here, which is iodine. That's in the overall equation, the iodine. Right? Now, does that work? That plus that makes HCl, yeah, and HI. HI, which will cancel out. Line through, which is good. But HI, it doesn't cancel out in the experiment, it just cancels out in terms of the overall equation. HI plus ICL, will make iodine and will give me HCl as my second product. That's your first step, the rate determining step. That's your second step to give you, when you add them together, the overall equation. Job done. That's the question answered. Okay, now we'll do one more. See how you go. I always find these quite tricky for me, but the students seem to get the sort of hang of it. We'll leave that there. We'll get rid of this. We'll do one more, so you've got them at least as a sort of a comparison. Okay? Let's do this one. Right, here's an overall equation. 2NO2 plus ozone. Doesn't matter, you've never heard of it, it's irrelevant. Make some weird thing, N2O5, right? Plus oxygen. And again, there are different answers for this. So have a play around with it. Right. Rate equation is equal to, from experiment, I suppose evolution of a gas is how you would measure, is how you would monitor the rate for this, if you're doing it experimentally. The rate equation is NO2, O3. First order, is it? Certainly is. Right, you should be able to come up with that now. You stick to your principles. Stop me, pause me, and think for yourself. Okay? If you don't think for yourself, you ain't going to be able to do it. All right? When it comes to the crunch. Okay? So have a go and then see if it matches what I'm going to come up with. Right. Where do I start? First order, first order. So, one particle in the rate determining step reacts with one particle of that to make whatever. Okay? Then look at the overall equation. What's left? Well, I've used one particle in my rate determining step. Slow step. I've got one left. To match the overall equation, I've got to put something in there. Plus. Okay? Then, let's see. Well, difficult for me to explain, but let's see. How about this? I've got to make N2, O5 and O2. So how about I do this? Intermediate, NO5. Intermediate that will cancel out because it doesn't appear in the overall equation. Put it in there. It doesn't take long. You play with these, right? What will that give you? Will that give you what you want? Sorted the rate equation out, sorted this side of it. I need to make this and this. And none of them can appear here because that's all used up. I can't make anything else, all right? So I'm forced to do this. I've got to make N2O5 and I've got to make O2 to match the overall equation. Does it work if I use that? Ooh. N2O5 plus, I've got oxygen left, O2, job done. That is the two-step suggested or possible mechanism for that reaction. Okay, so have a look at those, play with them. They are a bit weird, they are a bit tricky, but that's how you do them. Okay, that's how you do them. All right, cheers then, guys. Thanks for that. I'll see you later.